Next up, we have Xiaoheng Chen to present a general approach to define binders using matching logic.
Hello everyone, welcome to this video. My name is Xiaoheng Chen. My talk today is about a general approach to define binders using matching logic. This is a joint work with my supervisor, Professor Grigory Rasu. Our papers can be found at the links below. The technical report includes all the proof details in the appendix. The main motivation of the work is the K formal semantic framework and its logical foundation, matching logic. The K framework allows users to define the formal semantics of any programming languages. As shown in the picture, once the semantics is defined, all language tools such as parsers, interpreters, and verifiers are automatically generated by K. In practice, K has been used to define the formal semantics of many real-world languages such as C, Java, and JavaScript. K allows users to define the common language features easily, including binders. For example, the following K definition defines the syntax of lambda calculus. An expression is either a variable or an expression applied to another expression, or has the form lambda x lambda var.e. The binder is an attribute which will trigger the internal substitution mechanism in K to provide a correct implementation of capture avoiding substitution. Currently, this only works for a restricted form of binders, but with this paper, we can give the binder attribute a clean mathematical explanation, which will make K to support more general binders in the future. Mathematically speaking, every K definition is a logical theory of matching logic, where the syntax and semantics of a programming language are defined using matching logic axioms. So our job in this paper is to show how to define binders as matching logic theories. Matching logic is expressive. Many important logical systems can be defined as matching logic theories. These include first logic, separation logic, Hall logic for program verification, temporal logics, and many others. However, no logical systems where binding plays a major role have been thoroughly defined in matching logic until this paper. In this paper, we study the typical systems that include binders, such as lambda calculus and type systems. We define them as matching logic theories, and we prove that our definitions are correct by showing that they preserve the syntax, semantics, and formal reasoning of the target system. Here is an overview of the main contribution of the paper. Firstly, we simplify matching logic and propose a variant that is more suitable to define binders. Secondly, we use lambda calculus as an example and define it as a matching logic theory, gamma lambda. The key observation is that lambda xe does two things at a time. It creates the binding of x in E and also builds a term lambda xe. In matching logic, we separate these two. We first use bracket xe to define the graph of the function that maps x to E. Here, xe is the pair of x and E, and in matching logic, exists means union. So this pattern is the set of all pairs xe, where x ranges over the variables. The intension packs the graph set into one element, which then includes all the binding information. Then we define lambda xe by applying the constructor lambda to the graph set xe. The constructor builds the term. In short, we use the built-in exists binder of matching logic to build a graph set and create a binding, and then use constructors to build the term. To show that the above definitions is indeed correct, we prove the following theorems. We prove that gamma lambda is a conservative extension of lambda calculus, so any equations between two lambda expressions are provable in lambda calculus if and only if they are provable in the theory gamma lambda. We also show that gamma lambda is sound and complete, so semantic validity and provability coincide. One important advantage of our approach is that the theory gamma lambda automatically gives a class of matching logic models, and the following two theorems connect those models to lambda calculus. The representative completeness states that for any lambda theory, T, which is a set of lambda equations, there is a model MT of theory gamma lambda. such that MT captures precisely the lambda theory T. That is, E1 equals E2 is provable in T if and only if it holds in MT. The last theorem states that for any lambda calculus model A, there is a matching logic model MA of the theory gamma lambda that captures A. Lambda calculus has many different models. In this paper, we consider the models that are concrete Cartesian closed categories, or called concrete CCC models. The technical details can be found in the paper. To sum up, our definition of lambda calculus that first creates the binding and then builds the term is correct and captures lambda calculus faithfully. Then at the end of the paper, we generalize it to other systems with binders, such as system F, pure type systems, etc. In the following, I'll give a high-level overview of matching logic, including its syntax, semantics, and then, as an example, I'll define lambda calculus in matching logic. Due to time limit, I won't discuss the generalization part in this talk, but I'll be happy to address it in the Q&A session. Matching logic is a very simple and minimal and yet expressive logic. It is the logical foundation of the K framework. Its syntax defines formulas, which we call patterns, using only 7 constructs. They are element variables, which are like first logic variables that range over elements, set variables, which are like propositional variables in modal logic that range over subsets. Symbols are like set variables, except that their interpretations are fixed by the models and do not change. Phi1, Phi2 is the application pattern, where we apply Phi1 to Phi2. If Phi1 is a function or a constructor, then the result is like a first logic term. If Phi1 is a predicate, then the result is like a first logic atomic formula. But in general, any pattern can be applied to any other pattern, giving matching logic maximum flexibility. Next two constructs, bottom and implication, are standard propositional constraints. Other propositional operations can be defined from these two. Finally, exists X phi builds the existential quantification like in first logic. Now we move on to the semantics. The semantics of matching logic is one sentence. A pattern phi is interpreted as the set of elements that match it. In other words, patterns mean sets. Formally, a model M has a non-empty carrier set and a binary application function from M to the power set of M, which will be used to interpret the application pattern. Each symbol is also interpreted as a subset of M. Now, given a valuation that assigns element variables to elements and set variables to sets, the pattern interpretation phi rho is defined like this. For example, X evaluates the element role of X, sigma evaluates to the interpretation sigma n, bottom evaluates to the empty set, meaning that no elements can match it. Application is interpreted using the application function. But now, phi1 and phi2 are also sets. We range over their inhabitants by A1 and A2 and take the union of all the results. This is called the pointwise extension. Finally, exists X phi is interpreted by ranging over all elements A in M and taking the big union of all the resulting sets. In short, exists means big union in matching logic. In matching logic, we use theories to capture the target logical system, such as lambda calculus. A theory consists of two components, a set of symbols and a set of axioms that define the behavior of the symbols. We also define notations, which are just syntactic sugar. With the proper notations, we can capture the formulas or expressions in the target system as is without any translation. We say that a model M is a model of the theory gamma if all axioms hold in the model. That is, they are interpreted to the total set. Then, for each theory, we have a class of its models whose properties can be expressed by patterns. For gamma to correctly capture the target system, we need to establish an equivalence between the models of gamma and the models of the target system. Then we can use matching logic patterns to express and reason about the properties about the target system. In section 4 of the paper, we define the matching logic theories that captures many important mathematical concepts, such as equality, membership, the concept of sorts and many sorted functions, pairs, and the power sort 2 to the s, whose elements are the sets of elements of sort S. Based on these inference structure definitions, we now define binders in matching logic. We define the theory gamma lambda that captures lambda calculus. Due to time limit, I only showed intuitive ideas. Intuitively, the lambda abstraction lambda xe creates infinitely many alpha equivalent representations. Lambda x1 e, x1 substitute for x, etc. Our idea is to capture these representations. To do that, we construct an argument value pair where the first argument is the variable and the second is the substituted expression. Then we define this existential pattern. Recall that the semantics of existing matching logic means set union, so this pattern means the union of all pairs. In other words, this pattern is the graph of the function that maps x into E. To wrap up the definition, we take the intension of the graph set. The intension of the set equals to the set itself, but the set is no longer regarded as a collection of elements, but as a single element in the power set domain. This way, we can avoid the pointwise extension when we apply the constructor lambda to the set. We introduce the notation bracket xe to mean the intension of the graph set, which is one element that encodes all the binding information of x into E. And finally, we define lambda xe as the application pattern where the constructor lambda is applied to the graph set bracket xe. In short, to define lambda abstraction, we first use the built-in binder exists to define the graph set and capture the binding behavior. Then we build the lambda term using the constructor and the matching logic application. The correctness of the definition means that the encoding from lambda calculus to matching logic is faithful with respect to the syntax, semantics, and the formal reasoning of lambda calculus. In terms of the syntax, matching logic captures lambda expressions verbatim. The lambda abstraction becomes this pattern, where we use lambda to build a term and use bracket xe, which is the graph set, to build the binding. In lambda calculus, formal reasoning means equational reasoning plus the beta reduction rule. To capture that, we add beta reduction as an axiom schema to the theory lambda. Then we can prove that gamma lambda indeed captures lambda calculus faithfully, in the sense that lambda calculus reasoning is equivalent to the matching logic formal reasoning within the theory gamma lambda, and is also equivalent to the semantic validity within the theory gamma lambda. To conclude, in this paper, we gave a generic way to dealing with binding using matching logic. Since matching logic is the logic foundation of K, our work is useful to the development of K. In the paper, we propose a simple matching logic variant that has only 7 syntactic constructs, and we fully develop its model and proof theories. Then we define the matching logic theory for lambda calculus, where lambda abstraction is defined by applying the constructor lambda to the graph set bracket xe. We prove the correctness of this definition by showing the equivalence among the validity and the provability of lambda calculus and matching logic. Finally, we extended our approach to all binders in a systematic way, where the details can be found in the paper. Due to the time limit, I cannot fully cover all technical details in this talk. The paper and the companion technical report contain all the details. I'm happy to answer any questions about the work in the Q&A session. Thank you for watching.
Thanks very much, Xiaohong, who is now available in both the New York and Asia time bands for question and answer.